Chapter 29. Problem 20. Problem 20 wants to know what is the energy in joules and EV of a photon in a radio wave from an AM station that has a 1530 kilohertz broadcast frequency. So we have a frequency of 1530 kilohertz. And right away I'd convert that to just hertz. What is that in hertz? What is a kilo? Times 10 to the 3. Perfect. 1530 times 10 to the 3 hertz. And we want to know what is this energy in joules and what is the energy in electron volts. How do I find energy from frequency? You're gonna smack yourselves in the face when you realize this. H times F. So this question, how do I solve it? What's H? Planck's constant. It's your solution to all of this woman's problems. Just strap a Planck to her. So Planck's constant. What is Planck's constant? 6.63 times 10 to the negative 34 joules over seconds. And then we multiply that by the 1530 times 10 to the third hertz. It gets really creepy in here because the air conditioning turns off and I can hear everything. Multiply these numbers together and you should get 1.01 times 10 to the negative 27 joules, assuming I'm reading my handwriting correctly. That's it. Yes.
Why did we have to change
What was this
it?
hard?
I mean, we just changed to the SI. Is that?
SI.
Oh.
Okay. Questions on that? Now I also have to find this energy in electron volts. To find it in electron volts, I multiply this number 1.01 times 10 to the negative 27 joules. And I know 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So that's a conversion factor. Do that multiplication and you should get 6.34 times 10 to the negative 9 electron volts. So that would be all for number 20. Okay? If I put that on the exam, how many points is that worth? That's worth like negative 5. 100 if the exam is out of 10 million points. That one's pretty straightforward. Any questions on that one? Yeah. SI system, you use joules. It turns out a lot of times electron volts are more convenient when you're practically using them. None of you are going to practically use this, so as long as you can apply that conversion factor, I'm happy. No questions on 20 then? No. All right, let's look at number 62. 62 was quite popular as well. So number 62 says, if the position of an electron in a membrane is measured to an accuracy of 1.00 micrometers, what is the electron's minimum uncertainty in velocity? If the electron has this velocity, what is its kinetic energy? And then part C, what are the implications of this energy, comparing it to typical molecular binding energies? So part A, they give us an accuracy of 1 micrometers. What does that actually mean? Accuracy, what variable would that be? To help you out a little bit, this is in the section called the Heisenberg uncertainty principle. What equation represents the Heisenberg uncertainty principle?
Oh,
Change in X.
Change in X, change in P is greater than or equal to H over 4 pi, is it?
Yeah.
Okay, so what variable did they give us? They gave us change in X. The uncertainty in X is 1.0 microns. What should I convert this to? what is a micron? Times 10 to the negative 6. Good job. You're all better than my calc-based physics class. They don't know any of these conversions. And they're getting biology degrees to go to med school. Don't go to them when they become doctors. Okay, I need to find the minimum uncertainty in velocity. How do I find that? I don't even see a velocity in there. Air conditioning's back, so I can't hear again. P equals mv, right? So I can have delta x times m times delta v is greater than or equal to h over 4 pi, because p is also equal to mv. Then I can solve this for delta v. Delta v is greater than or equal to h divided by 4 pi, and then I also divide by the delta x and the mass. So delta v is greater than or equal to h. H is 6.63 times 10 to the negative 34 divided by 4 pi times delta x, which is 1 times 10 to the negative 6, times m. Ooh, m is the mass. What's the mass? Mass of an electron, which is 9.11 times 10 to the negative 31. How do we know it's the mass of an electron? That's what the problem says. It says it's an electron. So delta V greater than or equal to, multiply this all out, and you'll find 57.9 meters per second. Delta V. Any questions on that? So that was using Heisenberg uncertainty principle. That's how that equation actually works. And then we were asked to find what is the kinetic energy of this electron if it has that velocity. So how would I find kinetic energy? 1/2 mv squared. Go back to physics 1. It never goes away until you graduate, then you'll never see it ever again. 9.11 times 10 to the negative 31 times 57.9 quantity squared, and kinetic energy is 1.53 times 10 to the negative 27 joules. Is it just me, or does it sound like the building is blasting off? We are launching. We can also get another kinetic energy. We can get that the kinetic energy is 9.5 times 10 to the negative 9 electron volts. How do I get that? Do the conversion factor. 1 electron volt is 1.6 times 10 to the negative 19 joules. Okay? Any questions on that? If I give you a question and I ask you for the energy and I don't specify the units, does it matter which one you do? No. What's probably the easier one to do? Joules. Because if you convert everything into SI, what energy are you going to get out? Joules. Okay?
Did you say the conversion is 1 times, what is 1 electron volt?
1 electron volt
1.6 times 10 to the negative.
is 1.6 times 10 to the negative 19 joules. One electron volt is the energy inside of 1 electron. So 1.6 times, that's the charge of an electron. That's where it comes from. We learned that a ways back.
Oh yeah, it's Q equals Q. Yeah. That's Q, right?
Q, yeah, charge of an electron. Okay? Preguntas? No preguntas? Bien. All right, let's do the next one that was very popular for people to ask, number 77. Number 77 asks, what is gamma for an electron emerging from the Stanford Linear Accelerator with a total energy of 50 giga eV? Then find its momentum and find the electron's wavelength. Ooh. Gamma. What the heck is gamma? Well, first they told us this energy is 50 giga eV. What's giga? 50 times 10 to the 9 electron volts. This is very, very high energy. Linear accelerators, they shoot particles super, super fast. They shoot them close to the speed of light. If we're shooting things close to the speed of light, this means we have to obey relativity. That's the gamma that they're talking about, the gamma that we have for relativity. So Einstein likes to say E is equal to mass times the speed of light squared. But if you're going super, super fast, what is that missing? What do we need to add into there? Gamma. So energy is gamma times mc squared. They gave us the energy. Right, so I can shuffle this equation around and I can solve it for gamma. Gamma is E over mc squared. What should I probably do with that energy? I got 50 times 10 to the 9 electron volts. Do I want electron volts? No. What should I convert? Convert to joules. So do that Joule conversion. 1 electron volt on the bottom is 1.6 times 10 to the negative 19 joules on the top. Somebody multiply that out for me. What do you got? 8 times 10 to the negative 18 joules. Okay. So now I can take this gamma, and this is equal to 8 times 10 to the negative 18 joules, divided by mass. What kind of particle am I using here? What is gamma for an electron? So what mass do I plug in? Mass of an electron, which is 9.11 times 10 to the negative 31. And then C. What's C? 3 times 10 to the 8, the speed of light. Plug that in. What do we get for gamma? Looking at all your faces, I clearly need to go to a penmanship class. What'd you get?
9.76 times 10 to the negative 5.
Times 10 to the negative 5? Yeah. Okay. So then part B, that's what our gamma is. What are the units of gamma? No units. Completely units. Now part B asks us, what does it ask us? It asks us, find its momentum. So we need to find what the momentum of this particle is. Momentum is normally equal to mass times velocity. What happens when you're going really fast? You need relativistic momentum. Well, how do I get relativistic momentum? It's really easy.
Add a gamma.
Chuck a gamma in there. P equals gamma mv. How fast is this thing going? It's in the linear accelerator. It's being accelerated super, super fast. So we're going to assume that it's basically going more or less the speed of light. This to this is a pretty big jump. It comes from knowing what they do in particle accelerators. So now we got P equals gamma, which was 9.76 times 10 to the negative 5, times mass. What mass? Electron. 9.11 times 10 to the negative 31, times C, 3 times 10 to the 8th. So what do we get for P?
Times 10 to the negative 26.
Okay. Now they want to know, what's the wavelength of this electron? How do I find the wavelength? I just found the momentum. If I know P, what's the easiest way to find lambda? Lambda is h over p. H is Planck's constant, 6.63 times 10 to the negative 34 over p, 2.67 times 10 to the negative 26. Plug all that in, and what do we get? A number. There you go. There's your wavelength. Okay. For this one in particular, if you look at the solutions in the book made a mistake. You will have the same numbers out front, but your factors of 10, these 10 to the minus 8, those are going to be different than what the book answers are. These are the right ones. Any questions on that one? How many points is that worth? That's 10 points. Sure. 10 points. Plug and chug. Okay, let's do another problem then. Let's do problem number 4. A few people asked about 4. Problem 4, what is the longest wavelength electromagnetic radiation that can eject a photoelectron from silver, given that the binding energy is 4.73 electron volts, and is this in the visible range? So if I'm ejecting photoelectrons from some kind of metal, what kind of equation am I going to want to use here? What is this talking about? Kinetic energy of a photoelectron. So that's kinetic energy. What is that equal to? H times F minus the binding energy. And they gave us that the binding energy in this situation is equal to 4.73 electron volts. What's a good idea to do right away? Convert it. 1.6 times 10 to the negative 19 joules in 1 electron volt. So convert that right away. Get rid of the electron volts to get 7.57 times 10 to the negative 19 joules. And this is the reason we have electron volts, because it turns out in a lot of experiments you get nice numbers, 4.73 electron volts, so you don't have to worry about factors of 10. If you do this all in joules, you've got that times 10 to the negative 19, so it's a little messier. That's why we have the electron volts. Okay, and they want to know what is the, let's get the exact phrasing they use. What is the longest wavelength electromagnetic radiation that can eject a photoelectron? If I go to a long wavelength, that means I have low energy. So they want to know what's the lowest energy I can possibly have to have something get ejected. If I'm talking about the lowest energy or the longest wavelength, that means that I'm finding it for the kinetic energy. Basically, we want the kinetic energy of these electrons that are jumping to be just barely above 0. So if we assume that kinetic energy is 0, anything with the wavelength that gives us a binding energy that meets this situation is going to be ejected. So if it's a largest wavelength or minimum energy, you can assume kinetic energy is 0. So I can plug in 0. 0 equals h times f minus the binding energy. So hf equals binding energy. So the frequency is the binding energy divided by h. I was asked to find the wavelength. I have a frequency there. How do I find wavelength from frequency?
C over that. What's that shape?
Lambda?
Yeah.
Yeah, F is C over lambda. So I have C over lambda equals binding energy over H. Get my lambda by itself. Multiply my lambda to the other side, and then shift the H into BE back over. So my lambda becomes H times C divided by BE. So my wavelength is going to be 6.63 times 10 to the negative 34 times the speed of light, 3 times 10 to the 8th, all divided by the binding energy. Oh gosh, I can't read my own handwriting. 7.57 times 10 to the negative 19. Plug all those numbers in and you get 2.57 times 10 to the negative 7 meters. It's about 257 nanometers. This is in the ultraviolet. So it's not the visible range. What is the range of visible wavelengths? 400 to 700. So because this is lower than 400, it's smaller than violet. So that would be ultraviolet. Question on number 4. Nothing for 4? Going once, going twice. Sold to number 8. Let's look at number 8 now. Number 8. What is the maximum kinetic energy in electron volts of electrons ejected from sodium metal by 450 nanometer electromagnetic radiation, given that the binding energy is 2.28 eV? How do I find this? What equation? If I'm looking for maximum kinetic energy, what equation? Same equation. Kinetic energy is HF minus the binding energy. In this one, they give us a wavelength. They told us that wavelength is equal to 450 nanometers. That's 450 times 10 to the negative 9 meters. They told us the binding energy we have is 2.28 electron volts. 1 electron volt converted into joules, 1.6 times 10 to the negative 19. Gives me a binding energy of 3.65 times 10 to the negative 19. So now I have my kinetic energy equation equals H times F minus the binding energy. Did they give us F? No, what did they give us? Lambda. So I need to replace the F's with the equation that involves lambda. F is c over lambda. So the kinetic energy is also equal to h times c divided by wavelength, minus the binding energy. Do I have all these variables? Yes. Kinetic energy is h. H is 6.63 times 10 to the minus 34 times c, which is 3 times 10 to the 8th, divided by the wavelength, which is 450 times 10 to the negative 9, minus the binding energy, which is 3.65 times 10 to the negative 19. That'll give me a kinetic energy of 7.7 times 10 to the negative 20 joules. Did they want the answer in joules? They asked for it in electron volts. How do I get that into electron volts? Use your conversion factor. And you'll find your kinetic energy is 0.48 EVs.
If we wouldn't have changed it in the beginning to joules and just worked with electron volts, we've gotten that
No.
number? No.
Because this Planck's constant is in joules.
Okay.
So, if you found a version of Planck's constant that is in electron volts, you could keep that in electron volts if you want.
Oh.
There is, Planck's constant does have a version that's in EVs.
Yeah, in the book they use that other number.
Yeah, so you can use that. I've been pretty consistent with telling you always convert into SI, so that's what I show you how to do. That will always work. It's the minimum you need to know. Try not to throw extra equations and constants at you. Okay, let's do no questions there. Last one, let's do 51. And when we're done with that, we've almost done all your homework. Okay, number 51. At what velocity does a proton have a FM, that's a femtometer, wavelength about the size of a nucleus? Assume the proton is non-relativistic. Okay. So we need to find some velocity at which a proton, so we have a proton, has a wavelength, okay, of 6.00 femtometers, which is 6 times 10 to the negative 15 meters. So what velocity does my proton need to have to give me this wavelength? So I'm finding the wavelength of a particle. How can I find the wavelength of anything? An equation called de Broglie's wavelength. It gives you the wavelength of anything. As long as you know h and you know its momentum. What is that equation? Wavelength.
H divided by
H over p. And p is mv. So lambda is h over mv. So I can solve this for v, move my v over to the left, move my lambda over to the right, h over m times lambda. That'll give me the velocity that I get to get a wavelength that I'm looking for. So the velocity here is going to be equal to h. H is Planck's constant, 6.63 times 10 to the negative 34. All divided by the mass. What mass do I use? What kind of particle? Proton. What's the mass of a proton? We all know this off the top of our heads.
1.7 times 10.7.
Maybe we do know it off the top of our heads.
No, it's on the
It's on these sheets that I give you. Times lambda, 6 times 10 to the negative 15. Plug all those in, and V is equal to 6.62 times 10 to the 7 meters over seconds. Any questions on that? No?